What kind of crazy archaic C code is Ray going to dig up this time? Find out on today's episode of Craft versus Cruft. Now, it's only been 2 weeks since I last spoke with you. The last episode was RefactorGPT and the future of maintenance, and it just feels like so much has happened since the AI news cycle plows on. I have learned a whole lot over the last 2 weeks, a lot of which I'm going to try to very quickly share with you today. Ultimately, what we're going to get to today is a way of generating what I feel is some pretty useful API documentation using GPT 3.5 and some clever scripting. And if that weren't already useful enough, I think there are some pretty interesting implications for steps we could take beyond that. In order to accomplish that, though, we've got to get around a bunch of architectural hurdles, and I'm going to share with you the way that came about with some common techniques that are circulating out in the GPT sphere. So real quick, cutting through the alphabet soup, when we say GPT, that stands for a generative pre-trained transformer. And there's sort of this hierarchy of what contains what here. A GPT is a type of LLM, a large language model. An LLM is a type of deep learning neural network, which of course is a type of neural network, which is a field of artificial intelligence. So in particular, GPTs are like autocomplete, except they are really, really smart autocomplete. They're like autocomplete with the Infinity Gauntlet. It's Clippy with the Infinity Gauntlet. Go put that in DALL-E and Midjourney and see what you come up with. Send it to me. Now, as I said in the last video, a lot of fuss being made right now about the fact that these things can generate not just, textable manner, but some pretty cogent small blurbs of code under some contexts. So, are these the new programmers? Are they programmers' assistants? What that look like? And I explained a couple weeks ago why that's not the interesting problem to me. The interesting problem is, what are we going to do with all the code we already have that we need to maintain, and all of this new code that supposedly GPT is going to generate? What are we going to do with it? Basically, how are we going to solve the ownership problem? The problem with legacy code is really just that it's successful. The problem is that we're stuck with it. We depend on it. Oftentimes we fear to change it, and that's trouble. So whether or not AI can help us write new code is going to be irrelevant if our ability to maintain current systems, which is fairly inconsistent in the industry, if that doesn't improve. So what I'm very interested in right now is, can we use LLMs to help us get better at this? Now, last time I was experimenting with having GPT produce refactoring suggestions for a particular little block of code. I'm going to tackle something a little more difficult now: context loss. A leading reason that code becomes hard to change is because of institutional memory. The people who wrote it aren't here right now. They have moved on, what have you, or I've simply forgotten what I wrote 6 months ago, or why. So things become very difficult to change when the context is lost. Can LLMs help us recover this context? That would actually be huge. What would that look like? They seem to be pretty good at, I say comprehending, I say understanding text that they read, even code that they read, using these words kind of loosely here. Whether you could say that a neural network understands something, I think is very dubious, but it does seem to be good at changing the representations of knowledge from one form into another in ways that is very useful in summarizing things. It's not magic, but if we design workflows carefully that incorporate conventional algorithms and everything that's great about them, and humans and everything that's great about us, and LLMs, the unique kinds of value that they bring to the table, I think that there are some really interesting possibilities. Going to go over some of them. I mentioned limitations. While they're extremely powerful, LLMs are also very limited. If you think of them as just a replacement for what computers could previously do, or as a replacement for humans, you're going to make a lot of bad assumptions about what they can and cannot do. They are good and bad and a completely different set of things than either of those two categories. There's some strange overlap there. So they're limited in ways I'm going to describe, and we have to figure out ways around those. For instance, LLMs suck at math and other things that you would think a computer would be really good at. LLMs are not conventional computers, even though they happen to be running on them. So if you ask an LLM a relatively easy math problem, anything, remotely non-trivial, it's very likely that it's going to get it wrong. What do we do about that? There are some things we can do. LLMs also have a knowledge cutoff for whenever their training data was gathered. That for GPT-4 and GPT 3.5 is September of 2021. So that's the big knowledge cutoff. If you ask ChatGPT something after that, it won't know. Most especially, it won't know whatever proprietary information you might have lying around that you would like it to know about, right? That's not in the training set. Unless you train your own model, you don't have that. This one's big. LLMs make stuff up. Sometimes they recall a fact. Sometimes they invent a fact. They seem to be unable to distinguish when they're doing one and when they're doing the other. So you have to treat any output from an LLM as somewhat unreliable. And that's a really challenging one to deal with. Then we have something that dominates the architectural decisions you make when building larger apparatuses around LLMs is the prompt size limit. So 4,000 roughly tokens for GPT-4 and the default model of 3.5, though there's a longer one you can use. The token is what you see colored here. They don't operate in characters or words like we would, but they have these kind of thing that's halfway between a character and a word. That's token. So if you continued this for, a little over a page and up to 3,000 words or 17,000 characters, then you would have the prompt limit. You can throw that in a word counter, or OpenAI's got a nice tokenizer that'll give you the exact token count if you're wondering how your input's going to work. So the way we're used to designing processes are, usually able to deal with data a lot bigger than this. This is a little bit of a bizarre limitation for us to work on. We'll deal with that in a couple of ways coming up. This technique is just come out in the last few months, and it is sometimes called the React framework, but in front end, we also have something called React. So it's not React.js, right? Uppercase A, the ReasonAct framework, which basically turns a GPT run in a loop into an agent that can access external tools. And it is just a lot of cleverness, not a whole lot of code goes into making this work, but a lot of cleverness where you have the original prompt and you tell GPT, okay, this is the question that we're trying to answer, the task we're trying to do, but also you have these tools. So you could give the final answer, or you can use one of these tools. You could call a calculator, you can call a search engine, whatever it may be. You can give all sorts of different types of tools to this. We're still exploring the possibilities. But you just tell it, your answer can either be a final answer or an invocation of one of these tools. And if the GPT says, okay, my response is that I'm going to invoke this tool with this argument, then your script goes off and executes that on the GPT's behalf, gives it another prompt with the conversation up to that point, plus the output of that tool, and then the GPT just picks up where it left off. And it sort of acts like it's, acting as this autonomous agent while it's doing this. It's really interesting to watch, but really it's all just a matter of prompt responses running in a loop. And if you've seen the ChatGPT plugin store, for instance, we have it here calling Wolfram Alpha. That is an example of a ReasonAct agent. So that pretty well deals with the case of it being bad at certain types of tasks, we can just give it a tool that's better at those things, potentially, as long as we have an interface that's simple enough for it to use. But what about the prompt limit and the knowledge cutoff? Well, we can augment the knowledge using a technique called prompt stuffing with an external data source, such as, which really common, is embeddings. What embeddings are is they're from the world of natural language processing, kind of adjacent to this LLM world. So the way that would work is down here you've got your corpus of information. You've got some books, what have you. You see a lot of examples of, chatting with a PDF or what have you. You got your corpus of information, and you take an ingester that divides it up into blocks, and you use a transformer. There's a library called Sentence Transformer, for instance, for Python that does this, and it uses a language model to convert that blurb into a giant vector of numbers. And you store those in a vector store, some kind of database that's good at storing vectors of numbers. And those are called embeddings. Now, if you were to take a search query or a similar document or something like that and run it through the same embedding and get a vector corresponding to it in the same, space, and you queried the vector store using a similarity algorithm, you end up getting something that is called semantic search, which is like search, but also not like search as we know it, because we are used to search matching specific terms exactly or very closely, like with stemming. But semantic search will match if they're just conceptually similar, if they would normally appear under the same context. It's like it's got a thesaurus, only it's, even more fuzzy than that. An analogy I like to use is if you were searching for, I'm looking for a joke where a turkey was crossing a bridge. Now, in a conventional search index, it's not going to see anything about turkeys or bridges. But in a semantic search, maybe if you queried a vector store with the embedding of it, it would return, oh yeah, chicken crossed the road. That's sort of like a turkey crossing a bridge, sure. Good enough. So this happens to often be really good at retrieving the relevant data to a user prompt, even if the user is not using the exact right search terms in the prompt. They are asking for something of that nature. So you find all of the semantically similar documents in that embedding search when the user asks for something. And then this is the clever bit. You thought, oh, that was clever. This is the clever bit. You just put that right in the prompt that you give GPT, because GPT doesn't know all the stuff in the corpus, but it does know the part that came back from the search now because you're doing prompt stuffing. And then it will respond back as though it had that knowledge already. So that's pretty clever, and there are various other ways that can be set up, and there are YouTube videos that go into a great deal of detail. If you're interested, I'll link some in the description. So that is using embeddings and prompt stuffing. You can also use summarization, right? And there are a bunch of different ways that you can do summarization. You do it in serial. One that's particularly interesting, and I'm going to bring it back up later, is MapReduce summarization. So I've got this big, long corpus, once again, that will never fit in a prompt, much too big, but I want to get a GPT to summarize this whole thing, for instance. I can divide it into chunks, just like we did before, maybe overlapping chunks sometimes, summarize each one, so I have a much shorter version with the gist of every chunk, and then I can summarize the summaries over here, and, it all eventually boils up to one mega summary that's not very long, but has accounted for every piece of the underlying document. And this scales arbitrarily, right? As long as you're willing to just do more summarization calls to the LLM, then you can MapReduce queries across arbitrary amount of data, as long as you are able to reduce them in some way and aggregate the results. And summarization aggregates decently well. Now, we're going to use this one in the legacy code context a little bit later. So having done the RefactorGPT exercise and being able to get suggestions on little blurbs of code, the size that I could put in, I was very eager to try this, turning this thing loose on an entire code base. So I decided to start with a Kata that my friend Nicholas suggested, who runs understandinglegacycode.com, link in the description. Great blog about code mending. Love it. So this is called the Lift Pass Pricing Kata, and it deals with the difficulty in refactoring some code that violates separation of responsibilities and so forth. So the middle paragraph here is from the Kata here on GitHub, and it tells a little bit about what they're trying to accomplish, the new functionality they're trying to introduce, and why it's difficult because some code's not reusable. It's not really important, the details. You can look it up if you're curious. And then I've just done some typical prompting, role prompting first, act as an expert in software engineering, make a specific and actionable suggestion about the project in the current directory as it pertains to this request. Now, I'm telling you the current directory because I've placed it in a world it can interact with, right? I'm not letting it run arbitrary commands, though you can also do that. I wouldn't do it unless it was under supervision. But I'm giving it a couple tools here, a file lister and the ability to show the contents of an individual file. So I say you don't need to execute this request, only make a relevant suggestion based on the current state of the code. So I'm going to feed this into a ReasonAct prompter, and I was using a framework called LangChain to do this, which has support for a lot of the different facilities that we've just discussed. If you're doing some coding against OpenAI or various other related tools, I highly suggest checking out LangChain. It's really unified the vocabulary in the community, provided a lot of useful abstractions for people to build on. So check out LangChain. I learned a lot from it. So here I am running an agent executor, and it's in the framework, makes this pretty easy, but it is just the diagram I showed earlier. It's not doing a whole heck of a lot. You can script this by hand as well. I've given it that prompt, and it has a thought, which is, okay, I need to look at the code. And so it takes an action, file contents, lists pricing.py. Now, it should have done that. It should have listed the files first and discovered that this was the Java edition of the Kata. There's no pricing.py anywhere to be found, but it just got back, the result of the action is called an observation, got back file does not exist. So in the subsequent prompt, it realized its mistake. It takes the other action, which is more appropriate, and it gets back all of these. And it quickly determines one of these two is going to be what we need to look at. So, okay, it's going to look at both those files. I'm truncating the output a little. Lists main, and it decides it's not in main. I'm going to look at prices. So it correctly inputs the full path of this to the file viewer here and views the contents of it. Again, I've truncated it, and it then says something pretty reasonable about what part of the code is getting in our way here and what we should, a vague but reasonable suggestion about what we should do here. And this is ultimately the output from those, 4 or so GPT calls that happen during this narrative. Then we get the finished chain message from LangChain. So that's super cool, right? Like, you can give it all sorts of different tools, and it'll sort of figure out how to interact with them. This is if you've only used ChatGPT, without the new plugins feature. This is a pretty surprising moment, even though it didn't do a whole heck of a lot. So from a Kata, I think, what if I turn this loose on a real big, hairy code base, right? Let us invent the Duke Nukem Kata, right? Duke Nukem 3D was a first-person shooter released in 1996. It was a competitor to Doom. So we're looking at not engine.c. We're looking at right now 1/16 of engine.c. in the source code, which later came out to Duke Nukem 3D. That's about 600 lines. The entire file is several thousand. You're not fitting that file in a prompt. If you use the last thing we just ran on this, it will immediately choke. So what can we do? Well, we have more tricks in our toolbox here. I decided the Kata would be make the monsters bigger, or figure out what you would need to change, where in the code you would need to change in order to make the monsters bigger. So I tried, plugging in that ReasonAct sort of method again, give it, an embedding search, give it a grep tool. These did not work well for various reasons. Maybe you'll be able to have more luck, but I did not have much luck at all. So this gets me thinking, what is my process when I'm navigating a code base? How do we navigate a code base at scale? Because this is a skill, but we don't always think about what our process is. I end up trying to do the summarization technique, right? If we can't view all of the engine.c at once, could we summarize blocks of it and say, okay, give me one line about what this is about. Give me one line about what this is about. Give me one line about what this is about. And summarize the code, not into code, but into just a little bit of prose. And then, as you can see, this is exactly the same length of code, right, that filled all this, except now it fills just a couple lines. And you could very quickly read over this and say, hey, does this look interesting? We don't know everything it does, but does this look interesting to what I'm talking about? Should I look at this further or not? You or I could see very quickly, the way we cannot see here, if we're on the right track looking at one of these or not. And just like we can, GPT can as well. So if you do a bunch of this summarization and then simply feed it back the results of a bunch of the summarizations into one prompt, it's able to select, with relatively few tries, which area it ought to modify. It comes up with just a handful of correct candidates. And so this is a viable way to navigate the code base. It's much, much more effective than those other ways that I had mentioned at this scale. So once I had done that, though, I kind of realized that I was onto something more interesting than whether or not I'm going to get it to figure out where to go to make the monsters bigger, because this is a documentation engine, isn't it? Right? So if we did this by function, and instead of those one-line summaries from before, decided, let's have it generate one of these Doxygen comments. If you haven't seen that, they're like Java docs or others. They just, you comment in a particular format here, and you're able then to generate in the build process HTML page that looks like this. Let me just show you what we ended up generating as well. Like this is the full Doxygen page. This is what Doxygen docs normally look like, except this one would have been all blank. It would have shown these functions and the signatures, and then no descriptions at all, because there are no comments in any place that it would pick up. There are very few comments in this code base, right? But there are now in this version, because GPT has gone and created these Doxygen comments. And I was able to run this on the 100 plus functions in the engine.c file. And it, in a few minutes, produced comments for every one of those functions. And it used 25 cents of API usage. Now, it's not free. It's pretty darn cheap. And they're not, I'm sure, fully accurate. I found one or two that were wrong, just spot checking them. But most of them were pretty reasonable. I would love to, comb through at some point with some people who know what they're doing and really get sort of a hit rate on how many of these had a significant error in them. But, I'm aware that these are not perfect. They are, in my opinion, accurate enough of the time to be very useful. Also, as a note here, I used the tree sitter parser to go over the source code and chunk these by function. The tree-sitter parser library has some interesting properties for applications like this because it was developed for a text editor. It was developed for use in Atom, and then its successor, which is being worked on, called Zed. And that means that it is able to work on code that is not fully compliant with its grammar, right? Because code that's still being edited will not all be correct, and you have to continue to parse it and continue to be able to highlight the rest of the syntax and pick up where you left off after the error. Before that, I probably would have tried to use something like Antler or maybe a language server for the language in question. And now I think the really interesting thing here is this can scale, like not just in the terms of documenting many more little functions and doing this kind of micro docs, these API docs of broader swaths. Like, it is certainly effective to do that from a cost standpoint if you can deal with vetting the output. But also you can scale up your summarizations by combining little docs into bigger ones in this kind of MapReduce summarization style, and create like a hierarchy, a navigable hierarchy of insight. Here I'm showing a screenshot from this tool called Yorse, which can create graph visualizations based on source code. Well, like that, except if every level of that tree had meaningful descriptions of what was underneath it, and you could generate meaningful docs at every level of abstraction in a system. Like, that's really cool. It would never be as good as if experts in the current context edited and wrote it just perfect, but the fact that it can be generated so easily in a lot of situations that right now don't have anything of the kind, I think that is very interesting. So I mentioned LLMs have these drawbacks. How have we done on those? Well, they're weak at various computational tasks, but either by another process invoking the LLM or by using the ReasonAct trick to have the LLM reach back out to that other tool, you go with that, bidirectional connection there. I think we pretty well can address that. The knowledge cutoff, again, we have some interesting ways to attack that, as well as the prompt size limit. They do still make stuff up. And so you can minimize that problem, but I don't think it'll ever be completely eliminated. We just need a plan to deal with that. We need to accept that about the tool and only use it in situations where we're comfortable with that. We have ways of mitigating it. And you'll recall that the people do not produce 100% accurate output either. And yet we have ways of making very safe processes that involve humans that are ergonomic to us. I think with careful system design, we can handle the same sort of thing with LLM. In the case of this auto-generated documentation, a simple thing you could do other than code review that you should be doing normally anyway is that you just mark the provenance of this information. This is a doc that was generated by an AI. Take that for what it is. Every time I go to someone's blog or to Stack Overflow to get the answer to some programming question, I am engaging with information of very dubious provenance, and I understand where it's coming from, and I understand that I need to be skeptical about it. Nonetheless, it's very useful. So I've got this new website, which you're hearing about for the first time, called Mender.AI. I'll be gathering techniques like the one you just saw and others, so we can start to discuss what works, what doesn't work, how does this integrate with our existing tool chain. So I hope you'll join me in that. And remember what Lao Tzu said in the Tao Te Ching: with patience, the most tangled cord may be undone. Thank you.